All right, so we're continuing just walking through the steps for our single sample T-statistic. We're going to start on step 3 now, which is our computation step. Again, the thing I told you you're going to hear me say many times is the fundamental difference between a T-statistic and a Z-statistic is that in a T-statistic, we're going to use sample variance in place of the missing population variance. So the first thing we've got to make sure we have then is sample variance. If the problem gives you sample variance, well, then you don't have to compute anything. It gave it to you. Otherwise, we need to go back to our formulas from chapter 4 to compute this, which is sums of squares divided by n minus 1, or sums of squares divided by degrees of freedom, however you want to write that down. Sometimes you're going to find, particularly book problems, are going to give you standard deviation. So how do you turn standard deviation into variance? Because really we only want to deal with variance from now on. Well, just think about the symbols. The symbol for standard deviation is that for a sample, right? We're talking about samples. And that's variance. So how do you turn s into s squared? Well, you square it. So if a problem gave you standard deviation, square it, and you have variance. If the problem gave you sums of squares, compute the formula, and you have variance. And again, if the problem gave you variance, then you're just done. So increasingly, one of the things I've said in class before is you have to take an inventory. What did the problem give me? And how do I use those pieces to get my steps done? The hypothesis test questions are always going to give you enough information. There aren't going to be any trick questions where they give you the whole thing and tell you to do the test and you can't. You just have to figure out, how do I get there? So that's the first thing we've got to get, is our sample variance. The next thing then is to calculate error. Well, in our last chapter, that was called standard error. But again, we can't really compute standard error without the population variance. We're going to use the sample variance to estimate the population variance when we substitute it. Therefore, what we're really computing is estimated standard error. It's an estimate because the sample is estimating the population, so the sample variance is estimating the population variance. So we're putting this word estimated in front of it to delineate it as different, but the definition is the same. What's the definition? How much difference should we expect to see between a sample mean and the population mean due to just simply random factors, random chance alone? The definition is identical. We're just putting the word estimated in there because it's an estimate. Because we're making this estimate based on sample information, we have to change the symbol. Remember, whenever we're talking samples, we're using symbols from our alphabet. Populations use the Greek alphabet. So the symbol for this is our S. Remember, before it was a Greek S. This is the Greek S, this letter there. But we're just simply going to substitute that out and put the same little subscript of n under it, m under it. So this symbol is called estimated standard error. And the formula for it is still essentially the same. We're going to get sample variance over sample size and then square root it. It's essentially the exact same formula. We've just substituted in sample variance where the population variance would have gone. But it's going to tell us the same information. How far apart should these two means just be naturally due to natural randomness? Which then leaves us with the last calculation, which is, of course, for the T-statistic. So for our T-statistic, again, we're essentially doing the same job. So the formula is almost identical. We're just going to change symbols. So for our T-statistic, to calculate a T, all statistic formulas are a fraction with a numerator and denominator. The numerator always measures how much difference do I see in my measurements. So the sample mean minus the population mean. And the denominator always says, yeah, but how much of that difference is due to error? So now we're putting our estimated standard error down there. So 3 possible calculations, 1 for sample variance, 1 for error, and 1 for the statistic itself. So just like last chapter, the math is kind of the easy part of these for a lot of these chapters anyway. Which means that we only have 1 step left as usual. Step 4 is to report our decision. And this is exactly the same procedure as before. Once we've calculated our t-statistic in step 3, we compare that against our critical t values in step 4, back in step 2. And if we landed in the shaded areas, we reject. If we hit the critical regions, we reject. If we're in the body, if we miss those targets, we fail to reject. So we're either going to reject the null hypothesis or fail to reject it. Again, all semester, that's going to be the case with step 4. There's never any other choice to report for step 4. It's either reject or fail to reject the null. Now, reporting this decision in APA format is mostly the same, but remember, the sample size makes a difference in how the t-distribution is either, again, wide and flat or sort of more narrow and tall. So we have to report the degrees of freedom when we report everything else. So again, we're dealing with t's instead of z's. So for our APA, if we were asked to report that, we would say we have a t, and right next to the letter t, we're going to report our degrees of freedom. That's just, again, standard APA formatting. So if the degrees of freedom was 10, we would say a t of 10. That's kind of how we speak it. Equals, again, whatever we calculated, reported to 2 places as always, whether it's a whole number or not. And then the probability of making a type 1 error, this p is either less than or greater than our alpha level. So we would put a specific number in here from the problem. We would put our calculator result there, and we would pick one of those 2 symbols. Remember, less than means reject, greater than means fail to reject. And then we would pop our alpha level right in there. So those are our 4 steps for a 2-tailed single sample t-statistic. So in the next video clip, we're going to go ahead and run through an example and see how that goes for us. And then we'll flip it around to 1-tailed and try it all again.